fourth talk. Basically, so the idea is that I want to explain a lot of concepts that they appeared in the morning talks. And in particular, there are some of my students who have never done in this area. There are students of George that who has also never done in this, this topic, even so they are doing holomorphic foliation. So at least the first talk is going to be very expository. So there was a limit cycle in the poster of the conference. I'm going to explain how this is produced. So the basic idea is this. So maybe I put the corresponding differential equation, and then slowly I will tell you how plus 0.9 and then y. So if you take any software who make the trajectories of ordinary differential equations, you put in this equation there, you will get the figure. If you want one of the software which is very common, GeoGebra, you can try to download in your iPhone and trying to to visualize this differential equation. And actually, this one I did it some 12 years ago in order to kind of popularize this area of Abelian integrals in holomorphic foliation. And okay, so I want to reach why when we make the picture of this, the trajectories of the differential equation, we get this limit cycle at the beginning. Okay, so let me. Well, if I want to talk in the context of the holomorphic foliation at IMPA, I have to start. Let M be a complex, if you want, compact surface. But the point that I will try, I will just reduce it to the example that I have here. And F be a rational function on M. And really the context goes in this generality. So at the end of the day, the foliation will be just a fibration. F df, whatever it is, the fiber of F are leaves of this. So that doesn't matter what is this notation it is. And well, the things goes in this generality, but let's just try to go to more each time in a more special context. So projective space, and you can take also two homogeneous polynomial in the this is the projective space with coordinate y, z. The point in this projective space x, y, z, and then you take two homogeneous polynomials of the same degree, degree f, degree g. So this, so the fibration given by f over g is, let's say, my first examples of the foliation. And in order to land on the context of a lot of talks today, then simply put g. This is another monomial, z to the d. So let's say that this been d. And so my rational function will be f z to the d. And then restrict to the affine chart z equal to 1. So when you do this one, then we are in the case of what's called Hamiltonian. F polynomial in xy of degree less than or equal to d, but let's take a degree f equal to d. And then fibrate. So this is f minus 1 t complex numbers. This is the fibration, which the people, which in the morning talk call in Pawawa, this is Hamiltonian system and so on. But well, the context is, I wanted to say that it's general for complex surfaces and so on. Okay, and as I said, at the end, the objective is to concentrate on this example. And maybe for this one, I will make even more explicit. F equal to y2 minus x3, another set of monomials. So let's say, for example, this one. And if you have never made the pictures of the level sets of the polynomial, maybe you try to do this one. Again, if you have already downloaded GeoGebra in your iPhone, just put it, let's say, in this case. So this is the point that I will do in the complex context, but in order to visualize the things, I will take, let's say, real level. So for example, the real level in this case, minus 3 plus 3x minus t equal to 0, and the t inner. So if you may make the real picture in R2, then x, y, and you make for many different t's, you will get this kind of picture. 1 minus 1. There will appear this center, which appearing in the talks of this morning. And then there will be alpha-shaped curve. Oh, sorry, actually not this one. So this is the 0 origin. But the curve passing through 1 will be also singular. And then the other orbits. So this is the real foliation. Okay, so this is the foliation induced by FDF, this on R2. But of course, what it at IMPA is, it's very common to look for complex foliation. So this is, you look at inside C2. And I don't know how many people, how many students can prove this fact, that when you complexify it, then of course this is of dimension 4. So you will have two-dimensional Riemann surfaces in dimension 4. And so the issue of visualizing will be problematic. Actually, one of my first student, Everson, who made the visualizing these things when you project to three-dimensional things. But anyway, but okay, in mathematics, we have theoretical methods to visualize without seeing. But so let me make this artistic picture. So there will be Riemann surfaces inside C2. But the most important things that when you can discover is that f minus 1t, actually from the topological point of view, if you don't need really to visualize it inside C2, but you may discover its intrinsic figure, and its intrinsic shape is a torus. minus 1 point. And, okay, but, well. Okay, so let's, something also about this picture. It's appearing the word Hamiltonian. So actually, you can look also this thing as solutions to an ordinary differential equation. If you do, let's say, well, so in general, what I'm saying that from now on you forget all this general context. I will just the polynomial context. So you can write down the corresponding differential equations. In the case of, let's say, this polynomial f would be something like this. Then. And, well, what I am saying, the solutions of this kind are tangent to the level surfaces of f. And in the case of my example, of course, it is very simple. You just make this derivation. It will be 2y. And then with respect to x, minus 3 x2. There is also a minus here, so there will be plus minus 3. And actually, this is this piece. This piece of this differential equation. So I will try then explain the other pieces. So in any way, if you put in your computer to make this picture, you will get just this one. And you see that there is no dynamics, there is no accumulation, and so on, because the solutions of this guy, they are inside the level surfaces of f. Okay, so let's go to the next step. So I need families of cycles. In my example, for example, I can take this one. So delta t, the delta t's are inside f minus 1 t. These are, let's say, oriented cycles. So in the picture that I have made, and in the talks of morning, there was appearing this vanishing cycles. Another name is a continuous family of cycles. And if you have done a holomorphic foliation course at IMPA, maybe delta t, a cycle with, so all these terminologies, they are the same. And not vanishing cycle is more specific, but anyway, these two are the same. The cycle with identity holonomy. And in a minute, I will try to explain this. But for the moment, you can take this family of cycles. And in particular, I will need this 0. There is also a cycle here, who is tangent to y-axis. So this will be my delta 0. So my delta t is inside f minus 1t. Okay, so I will need this family of cycles, which are appearing, for example, in the center focus problem of Lubomir Gavrilov. This can be the cycles around the center. And in the case of Darboux system of Pavon and Mardezek and Collin, there was this logarithmic differential equation, and then in the middle there was a family of circles. Okay, so let me keep this one. Okay. Well, if you are you are just doing holomorphic foliation and you don't care about, let's say, too much the real pictures, then you have to make a picture like this. Then you have to consider a leaf. Leaf will be, let's say, a two-dimensional object, and so the nearby leaves also there will be cycle. So you can lift up this cycle to nearby fibers. So, but really the thing that I'm going to tell is independent of real or complex context. I mean, the complex context, you have to just visualize the things. You don't have exact picture. Okay, so another thing that I need that during the talks of today appearing, let's take a small transversal section. In this real context, it will be just a small neighborhood of 0 inside real numbers. And in this case, again, my transversal section is of 2 dimension transverse to another 2-dimensional object inside 4 dimension. So this will be a neighborhood of the complex number inside C. And so let's make the holonomy map. So the holonomy, if you have not done course of holomorphic foliation, is the old name for this one. Somebody knows? Poincaré. First return map. And so, let's first explain in the real context. So the idea is that, for example, in the case of this fibration, if you look this one as a differential equation, you start from here, you follow the trajectory of the differential equation, and you return back to the same point. And then you say that the holonomy has identity. And in the same way, you can define in the complex context. And maybe in this Poincaré first return map, maybe in the real context one uses, but this one uses in the complex context, but they are the same concept. And so far, this concept of holonomy is trivial. But so let us a little bit complicate more. Maybe let me say another way of writing. So in the talks of today, this was appearing as polynomial pxy. This one appearing as polynomial qxy. But this is written as so there are many different ways to talk about the same object. One was this one that I am already using. The another one is as Lubomir did, just make the quotient dx over dy, or the vice versa, q divided by p. Or a more modern way, when you have the notion of differential form, then you write in this way, p dx minus q dy. Dx over q. Oh, sorry, okay, exactly. P over q, and then q dp. But actually, I will use the notion p dx minus q dx. Okay, anyway, this is the common notion of the foliations given by one form. So so something which appeared in the first talk that so the Hamiltonian one, df, has no dynamics, but you can perturb it to arbitrary differential one form. And this will have dynamics in the sense that, for example, there will be trajectories, for example, accumulating on this point. And I will use this notation, but in Mardezi and Cullen notation, it was using eta. So epsilon will be a very small parameter. So the idea is that I will take this one parameter family of, let's say, foliations passing through df, and let's see what happens to this, to the original foliation. Something that you will first discover is that the cycles are no more identities. So let me try to make this two picture again. So for the original foliation, when you were taking something very important. I don't know if it was mentioned in the first talk or not. Sigma. This is very important because the formula works with this one. Sigma is parameterized by the image of F. You see? So the coordinate system on the sigma will be the image of F. Okay, so when you consider this this perturbation, and then around this cycle there is no singularity, then you have the trajectory that I will call it delta t. Let me, in a minute I will fix the name. And then when epsilon is enough small, and then when you return back to sigma, so you will return back because your perturbation is the perturbation of df, which has an orbit which closes. But the point is that in the perturb one, you will not reach t again. You will reach another point. Let's call it h epsilon t. And this is the perturbed Poincaré first return map, or let's say perturbed holonomy. So you will have this map. Again, this sigma is also, I don't consider it global. Each time you can take it smaller and smaller for your purpose. So at the end, you will get this map. And so it's not identity, but if h epsilon at some point, let's say t0 is t0, and h epsilon is not identity, then you will get the concept of limit cycle. We get a limit. Well, roughly speaking, because I have to add that all the trajectories accumulate. So, but the point is that if at least for one value, you will this orbit closes, and for other values it doesn't closes. This means that you will have a closed orbit such that the others they are winding around this closed trajectory, like the one in the poster. So at the end, the perturbed holonomy, its fixed points controls the number of let's say this closed orbit or limit cycles in our context. Okay, so so let's call this one, let's say T, H epsilon T. So something that in the first talk it appeared. So you want to control the fixed point of this one. And since we started from analytic context, this you consider this difference. So you are looking for the zeros of this function. And I think in Pavon notation it was delta epsilon t. So everything is analytic. You can argue that it started from polynomials. The solutions become the holomorphic, given by holomorphic function. At the end of the day, this is holomorphic. You can write down its Taylor series at epsilon. So for epsilon equal to 0, H was identity, so the first term is 0. But from the next term, you will have something non-trivial. And then these are the word Melnikov function that were appearing in the today's talk. And something, okay, so well, if you are familiar with a little bit basic fact in complex analysis, you will see that at the end, in order to control the zeros of this one, you are supposed to control the zeros of the first term if it is not identically zero. But in a minute, I will reach to there. And okay, so let me write two propositions. And the rest of the talk, I will just write these two propositions, which their proofs are a kind of classical statements in the area, but maybe for those people who, for the first time, see this kind of thing is good. First of all, M1T. You have the formula for M1T, which was already mentioned. Depending on the orientation of the delta T, usually I orientate anti-clockwise in the real context. This is omega 1. So omega 1 is the first, and then our delta T. So this is the first proposition. I think I will try to prove it, because as I said, it is for mainly for students. The second proposition, I am interested in the zeros of this guy. So the zeros of this guy, if it is not identically zero, controls the zeros of this one. So let me write if M. Something also. Let's now forget the real context. And the complex context, the zeros, they never disappear. No? This is the good thing of the complex context. So if M1, maybe I write it without multiplicity, make it easier. Okay, just imagine that in M1, T0 is equal to 0, but M1 itself is not identically 0. If this happens, then there will be a fixed, a zero of let's say, this function h epsilon t minus t near to T0. And of course, for the statement for any for a sufficiently small epsilon, there will be always a fixed point of h epsilon near to T0. Okay, you can do a little bit actually in complex analysis. If this zero is of multiplicity n, there will be actually n zeros counting with multiplicities. And if you are in the real context, there is also this issue. Maybe it has multiplicity n, but some of the zeros jump up to the complex domain. But for my picture, I don't need to do this context. So the moral of the story with these two propositions, and this was the one which appearing in Collins' lecture. If I find more zeros for M1, this integral, I will get more limit cycle. And Hilbert 16 problem asks for the number of limit cycle and so on. So then you can introduce a weaker version of Hilbert 16 problem, which is known as the infinitesimal Arnold Hilbert problem, which involves the counting of zeros of Abelian integrals. Okay, so as I said, since this is mainly for students, I will try to prove this Actually, the proof was kind of not so explicitly was, for example, in Collins' talk, you were seeing that you restrict the differential form to some places and so on. Basically, it's like that. Maybe before proving that now, I am already ready to explain the differential equation there. Maybe I do this one, and the rest of the time I invest on this one. Okay. So let's return back to my differential equation. So the idea is that I want to prove to use these two propositions and make a perturbation of this guy, such that so remember that the picture was like this. Sorry, no. And this one tangent to the y-axis is delta 0 because it is in f minus 1, 0. So I want to just find the perturbation which somehow one integral is 0. And at the end, if you play a little bit similar to what Colin was doing at the end of his talk to obtain n square minus 1 limit cycle, then first of all, I have to consider as some deformation plus epsilon. And for the reason that I want to get some zero integral, I will put parameter s. So the idea is that I will make this perturbation and will choose s in such a way that I get a 0 of the differential equation. And so the epsilon will be the parameter of the perturbation, and the s, I will handle it to get this 1, 0. Okay, so this is a kind of just trying to play around. And from where I get these monomials, you will see in a minute, because I want to compute certain integrals, and in a minute it will be here. So I want that for this differential equation, m10 equal to 0. So this means that around the delta 0, I want to get limit cycle. And but according to so this is the thing. But what is m10? M10, the integration of delta. So let's write down the rest as differential form. It is x2 dy minus sy dx. So I want that this integral to be 0. And that's why I inserted s there. Oh. Recently my eyes x2 to the 2 dy. Yeah. And the reason why I inserted parameter s, because if I want this one equal to this one, I can compute s. Actually, this kind of computation was also implicit in Collins' talk. So this means that this will give me what? S equal to minus. Okay. I will use also Stokes' formula because I want to compute explicitly these periods integral. So as the Stokes formula, what will say? So this is delta 0. So the inside of this delta 0, let's call it capital delta 0. So let's use Stokes' formula. So this will give x dx y dy minus, actually plus s dx dy over delta 0. So this will be 0 if and only if my s will be delta 0 x dx dy delta 0 dx dy. So for example, you see that this is the volume of delta 0. And actually, this is an explicit number. And actually, this is even computable. In order to make a, for example, this had to do with the values of gamma function. Let me write also these things because sometimes gamma 7, 12, gamma 11, 12. For example, if you do put it Mathematica algorithm have implemented a lot of formulas, so it will give really this formula in terms of the gamma function. And of course, you can, even without this one, you can compute this one. This will be 0.9, 0, 25, blah, 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 blah. So it's a transcendental number a priori. So, but the idea is that if you, so in our context also, the things are, so let's say, we are in a perturbative case. So if I approximate S enough, and for epsilon small, then I will get a limit cycle. And actually, even in this context, it's not necessary to put epsilon equal very small. Even putting epsilon equal to 1 and S equal to 0.9, it will work, and you will see the limit cycle. So this is how the limit cycle is produced. Okay, so now you know at least the poster of the conference from where it comes. But of course, there are a lot of other ways to produce limit cycles. The question that I asked Colin is the recordist in lower bound for limit cycles. So he has one uses other methods. But let's say these limit cycles are specific to the zeros of Abelian integrals. Okay, so let me just in the rest of my time try to concentrate on the proof of this one. This is a kind of a very crash course on this small topic inside the topic of holomorphic foliation. So I think this one is this is much more important because the idea is that in the next talk I want to explain that this Francois algorithm, which appeared in many talks, it will give MIs, but that you can give also better formulas in terms of iterated integrals. So let's prove proposition 1. Again, you can do in a complex context, but I think in the case of real context, at least you have a better visualization. But in the complex context, it is the same. So I call this one L delta T H epsilon T. Okay, so the proof is so I have my foliation. So what is the definition of this curve? This is the curve such that when I restrict this guy, on top of it, it is identically 0. So this is the definition of the leaf. Delta T H epsilon T. This is identically 0. So the leaves of the foliations are one-dimensional curves which glue to each other, and their main property is that they are tangent to the kernel of this differential form. And then the proof becomes almost immediate. So let's now analyze this one. Okay, this one here. So we have an exact differential form. So what df, this one is identically 0, then its integration is identically 0. So exactly. Now, what I'm saying, so this is identically 0. In particular, if you do this integration, it is identically 0. So I don't need here. So this integral is 0 because this restrict to this one is in 0. Okay, so let's do the computation. So I will do computation up to epsilon squared. So this means that these terms I will not write. So df integrated over this one, df is exact. It will be f h epsilon t minus f ft. Then plus epsilon integral omega 1 delta t epsilon t. And the rest of the term, they have epsilon 2, blah, blah, blah. I don't care. At the end, I will compute the coefficients of. But remember that I told you parameterize the image, you parameterize this transversal section by the image of f. Well, if I am in the real context, let's go with it. But it's the same. So what this means that if f h epsilon t is the h epsilon t itself, if you consider h epsilon t as a number. So this will be h at the end that I will get h epsilon t minus t plus epsilon so we are already done, no? Remember that this one was m1 t epsilon plus epsilon squared, blah, blah, blah. And then coefficients of epsilon will give the formula m1 t plus. And when you put it epsilon equal to 0 here, then you will get the cycle delta t. So this is the why Abelian integrals pops up in the in this context. So actually, I have time for the other one also. Maybe I just mention this one and then I finish. Okay. Proof. This is also easy. In the at IMPA there is a complex geometry course. In the old versions of complex geometry course given by Camacho, Alcides, and Movasati, it was called several complex variables. And then so the theorem that you learn in the several complex variable is called the Weierstrass preparation theorem. So maybe I mentioned this one, and then we finish it. So just consider f epsilon t, what it is, h epsilon t. So the idea is that I will remove one epsilon, and still this will be, and let's work on the complex context. It still will be this holomorphic function. Oh, okay, exactly. GFF is already used. And then one of the things that one learns in complex geometry or several complex variables, if you have a holomorphic function in many variables, and you, let's say, you put, for example, in the general context, this can be also n-1 variable. If you, for example, put n-1 variable and one variable here, and then you look for this one, and you see that it has, let's say, multiplicity. It starts like this, t to the n plus something coefficient t to the n plus 1, and so on. So as a function in one variable, it has multiplicity n, so this is not equal to 0. So the idea is that putting back this n minus 1 variable again, then this n zeros will not disappear. So Weierstrass theorem, what will give? It will give you g epsilon t. You can write it as g tilde epsilon t. This is holomorphic in C20. This itself does not have 0, so g tilde 0, 0 is not 0. And then the rest will be polynomial in t, so t to the n plus g1 epsilon t to the n minus 1. Let me put here n minus 1. What? I am writing, this is in Tn. It will be polynomial, no? Because let's say the gi 0 will be 0, and at the end, if I put epsilon equal to 0, I will get some non-zero function and just multiply it with Tn. So maybe let's write it completely and then 0 epsilon t. So I think the basic idea of the Weierstrass theorem is that in T, modulo some function which is holomorphic and non-zero, this G will be polynomial in T. And, oh, sorry, let me say, there is no, exactly, you're right. There is just epsilon. There is just epsilon. Gi 0. So this polynomial t, when you put epsilon equals 0, will be just t to the n, which has n zeros of the multiplicity. And then when you perturb it, and anyway, this in the complex context, this n0 will not disappear. But of course, you have to a little bit discuss further because you are interested in real zeros. And then at least when the multiplicity is simple, then you can claim that the 0 will not transform into complex 0. It will continue as a real 0. And then, so the proposition will be proved saying that anyway, near to epsilon equal to, for epsilon small enough, you will have n zeros up to multiplicity. So this will be n fixed point of this one up to multiplicity. And then you are done. Okay, so I think I will stop. I want to make a comment about Ilyashenko's theorem because in some sense this is the origin of many discussions. But so the next talk I will talk mainly about this Francois algorithm and its version in terms of iterated integral. Any question? Now I am the chair. So, student, Felipe, entendeu tudo? Ah? Okay. So, if there is no question,